Here it is, net force 5. I think that this is probably just a one-day assignment. I did give you 2 days in this, the current version of, well, depending on when you're watching this, I suppose. It's always a good idea to go back and redo other problems from past assignments, especially the ones that you found to be more difficult at the time, to practice doing them. Because likely you're going to see things on the test that are like those. All right, so anyway, net force 5, here's some more practice for us. Suppose a hanging 1.5 kilogram mass here is attached pulley and string kind of situation. It's a half Atwood's machine, right? To a 5 kilogram block up here. This does not say specifically to make force diagrams. Probably on the test I would, so we're going to do that here. I'll make them kind of close to the objects here. So force of gravity on this mass times 10. The normal force would be equal to that because I ain't moving up and down, right? And then there's a tension force, and I don't know what that is right now. And for this one, the force of gravity on this block is mass times 10. And then there's force of tension, which is going to be losing because I know when we release this, this is going to start accelerating downward. I was going to write an equal sign there, but I don't know what that's equal to. And I know that it's the same string, so the tension forces cancel out. And that's important to know if you're going to do the sort of shortcut method here. Oh, and there's friction. Oops. On this block here. So there's a force of friction. And I'm going to go ahead and figure out what that is and put it up in my diagram. So the force of friction is equal to mu, which is 0.25, times the normal force, which is 50. And that's about 12.5 newtons. So that's this. Didn't leave myself much room there, did I? 12.5 newtons. Okay, so what's the acceleration of the block? Now that we know that, I know that if I'm going to do the unbalanced force total, do this method, is equal to the mass total times acceleration. The unbalanced force total, well, these cancel each other out. These tension forces cancel each other out. And so I have this winning, the force of gravity that's on the hanging block, minus the force of friction. This is the only one that has friction on it, so I don't feel like I really need to say that it's the block up top. You could, but there's only one friction force, so no possible confusion there. Is equal to the mass of the block plus the mass of the hanger. I'm just writing something different. Instead of mass total, you can just write mass total again there. And the 15, because that's the force of gravity on the hanging one, minus the force of friction. Total mass 6.5. And what do we get there? Got 2.5 divided by 6.5. About 0.38. Is our acceleration. That's how you do that. You got to think that there's going to be a problem like that on the test, right? What would be the minimum value of the coefficient of friction in order for the block to remain motionless? Well, if it's motionless, then all the forces are balanced. I think you could do this kind of just thinking about it and not necessarily redrawing all the force diagrams. But I'm going to go ahead and do that because, you know, I'm your physics teacher and everything. So force of gravity on the hanging mass would be 15 newtons. Now, remain motionless, what does that mean? That means that forces are balanced, right? If something's at rest or moving at a constant velocity, that means the forces are balanced. So the force of tension here would have to also be 15 newtons if it's going to be balanced. And then we look at the block up on the table, force of gravity is still 50 newtons, and normal force still balancing that. But the tension force is going to be 15 newtons because it's the same string, right? So that has to be the same as this. And then if it's going to be motionless, then the friction force would also have to be 15 newtons. All right. So what would the mu have to be? Well, I know that force of friction is equal to mu times normal force. If you're doing anything with this mu, I mean, this is the only equation that has the mu in it, right? So there you go. It's got to be that one. So 15 force of friction is equal to mu times the normal force on that block is still 50. So the mu would have to be 0.30. So it'd have to be a little bit more than that. The bigger the mu, the stickier, the more friction-y your surface. All right. Number 2. A block with a mass of 30 kilograms is moved at a constant speed, which means that forces are balanced, over a horizontal surface by a force of 50 newtons applied parallel to the surface. So this is like pushing a box across the floor, right? Construct a force diagram for the block. That's a big block. 30 kilograms of block. Force of gravity, 30 times 10. Normal force. It's being pushed by a 50 Newton force. We'll just call that force of push. And at a constant speed, so there must be friction equal to that. Could make some little geometry marks on there. All nice and up and down are balanced, left and right are balanced, and the coefficient of friction, that's the only equation that's got it. So force of friction is 50 is equal to mu times the normal force is 300. So mu is equal to 5 over 50 over 300, 5 over 30, 1 over 6.17. What would the acceleration of the block be if mu was 0? Well, if mu is 0, then there's no friction force. Mu equals 0 means friction is 0. So that would go away, and that would mean that the unbalanced force would just be that push, nothing else, no friction. So that's unbalanced force equals mass times acceleration. That's the mass in kilograms. The force of push is 50, so the acceleration would be 0.6 meters per second squared. Number 3. A 100 Newton force is applied to a 50 kilogram crate resting on a level floor. Coefficient of kinetic friction, sorry, I meant to delete that. We're just talking about, when we say coefficient of friction, we just call it the coefficient of friction. I'm sorry if that confused you at all. Coefficient of friction is 0.15. Draw a force diagram to represent this situation. I always make things, whenever there's a push, I always make it to the right. Do you do that too? Force of gravity on this, its mass is 50 kilograms, so 50 times 10. This 500 newtons of gravitational force. The normal force is going to balance that because there's nothing happening in the up-down direction. Moving this way. Let's see, what else? A 100 Newton force is applied. I'm going to call that force a push again. And then I've got a force of friction. And that's how we find the force of friction. So the force of friction here is going to be equal to mu, which is 0.15, times the normal force, which is 500. What's that? 500 times 0.15, 75 newtons. What's the acceleration of the crate? Well, the unbalanced force is that force of push minus force of friction. And Newton's second law is unbalanced force equals mass times acceleration. So that's mass times acceleration is equal to 100 minus 75. That's 25 divided by 50 is a half. In the situation described above, if the coefficient of friction was 0.25, is the 100 Newton force sufficient to cause the crate to accelerate? Draw a force diagram, then explain why or why not. So these things don't change because there's no motion in the up-down direction, so those are still the same and they're still balanced. And I still have the pushing force of 100 newtons. So what I need to do now is figure out if the force of friction is equal to mu times the normal force, then if that mu was 0.25 times the normal force, that's 125 newtons. Now, does that mean there's 125 newtons of friction? No, it doesn't, because that would be completely insane. Why? Because if there was 125 newtons of friction, that means there would be an extra unbalanced 25 newtons of force in that direction to the left, which would mean somebody would be like pushing on the crate, and the crate would be like resisting so much that it actually accelerated backwards. Like, that is totally impossible. So what does that mean? Well, if something's not moving, friction is as much as it needs to be to keep it still. So is this enough force to overcome? Like, you would have to have at least this much force to move this thing. Is this enough? No, it's not. So what does friction do? It matches that and keeps it from moving. Explain why or why not. So what's the question here? Is it sufficient? The answer is no. Because need at least 125 newtons to move the crate. All right, and then we got a last one here, a rampy kind of problem. 10 kilogram block is allowed to slide down a ramp. Looks like 20 degrees. It says make a force diagram here. I'm going to do it kind of over in this space here. I'm going to try to match that angle. If you want to like make it as an extension from here and then make your force diagram, that's not a bad way to do that if you have room to do that. Then I'm going to drop the gravitational force straight down because gravity doesn't care about ramps or anything. So the force of gravity is 10 times 10 rather, which is 100. Now everything else in my force diagram is going to be lined up with these axes. First thing I'm going to do, just like I'm plotting a point to get to here, x, y, x, y. And this is my 20-degree angle. So I'm going to do, I got to do 100 sine 20 and 100 cosine 20. This is the kind of thing when I was talking about practicing problems. Just make sure I'm in degree mode. This is the kind of thing you practice, right? I mean, after you do this a bunch of times, this is the same every time. You know, it's not like, oh no, I don't know what to do with this ramp problem. Well, it's the same as every other ramp problem that we've done. So if you're still not good at those, it means you need a little more practice. Or a lot more practice, maybe. So it looks like 34 and 94 are those components. Now, what about the other forces? Well, the normal force is perpendicular to the ramp. It's going to be straight up my little axis there, and that's got to be equal to this because there is no motion in this direction. The motion is this way. So that's going to be 94 newtons. How much friction is there? Well, the friction is going to be up the ramp in this direction, and that's going to be 0.15 times the normal force, (14 newtons). All right, what's the acceleration of the block? Well, it looks like my winner-loser direction. I got this winning, this losing, so the unbalanced force is the force of gravity, but it's this down the ramp part. That was the sine component. It's always the sine component, minus the force of friction. Now, unbalanced force, Newton's second law, is equal to mass times acceleration, 10a. The sine component of the gravitational force, winner minus loser. So that looks like 20. Hey, we got an acceleration of 2 again. There you go.